All right, this is lesson 24, example problem 1. We're given the cross-sectional area of a column and then asked to find the slenderness ratio, critical stress, and critical load for the column based on heights of 1 foot, 10 feet, and 50 feet. We're told it's made of A36 steel with a yield stress of 36,300 psi and a Young's modulus of 29 times 10 to the 6th psi. So the first thing we're going to do is we're going to convert all of these lengths to inches just so that our units are consistent throughout the entire problem. It's going to save us having to constantly come back and do that later. All right. So it also tells us that the column is fixed at both ends. It says pinned, right? So that tells you that the effective column length factor is going to be equal to 1. You can get that if you just go to the slides and you look at slide number 7 for Euler buckling and the effective length. The K value for fixed at both ends or pinned at both ends is 1. All right, so the first thing we're going to do is we're going to calculate the moment of inertia about both the x and the y axis for our column. So that's base times height cubed over 12 and base cubed times height over 12. So we go ahead and plug in 5 inches, 10 inches cubed over 12, and then 10 inches cubed, 5 inches over 12. Gives us a moment of inertia about the x-axis of 417 inches to the 4th and about the y-axis of 104 inches to the 4th. All right, next up we're going to calculate our area. Area is easy, base times height gives us 5 inches times, 5 inches times 10 inches gives us 50 inches squared. All right, so now that we have both our moments of inertia, we're going to calculate our radius of gyration. Right, so radius of gyration is just another measurement for determining the strength of our column in the x and the y directions. So it's not super complicated. Square root of moment of inertia about the x-axis divided by a, square root of moment of inertia about the y-axis divided by a. So 417 inches to the 4th over 50 inches squared, 104 inches to the 4th over 50 inches squared, square root. And if we check our units, inches to the 4th divided by inches squared gives us inches squared, and then we take the square root of that, we'll get inches, which is good because that's what we want. So we get 2.89 inches and 1.44 inches. So at this point, we're going to look at which of our radius of gyrations is smaller, right? So obviously that's going to be Ry. So that's going to tell us the column is more likely to buckle in the y direction, or that it buckles in the y direction at a lower load than it buckles in the x direction. So all of our calculations, we're going to use Ry because that's the weaker direction. We're going to use the weaker direction to determine the limits on our column. All right. So the next thing we're going to need the C sub C value. That's going to be required for helping us determine whether the column is short, intermediate, or slender. So that's going to be 2 pi squared times Young's modulus over the yield stress square rooted. So 2 pi squared times 29 times 10 to the 6th psi over 36,300 psi square root, and that gives us 126. So that's going to be useful later when we're determining what kind of column we have. All right, so the first one we're going to do for our L equals 1 foot column. So we're going to find our slenderness ratio, which is going to be K times L over R sub Y, which is going to be 1 times 12 inches over 1.44 inches, which is going to give us 8.32. 8.32 is less than 10. Therefore, it is a short column. For a short column, the critical stress is equal to the yield stress, which is equal to 36,300 psi. So that was pretty easy. And then if we want the critical load, it's just the area times the critical stress gives us 50 inches squared times 300 psi, which is going to give us, I'm just reading this off, 1,815,000 pounds. All right, so pretty high. All right, so next up we'll do our 10-foot column. We'll see how that compares to the 1-foot column. So again, slenderness ratio, K times L over R sub Y, 1 times 120 inches over 1.44 inches. You might have just noticed that this is the slenderness ratio from the previous one multiplied by 10, so 83.2. So 83.2 is in between 10 and our C sub C value, so that tells us that this is an intermediate column. So for an intermediate column, I'm going to move over to the left side just because I'm going to need a lot of space. The critical stress is equal to the yield stress times 1 minus KL over R squared all over 2 times C sub C squared, close brackets. All right, so you might notice K times L over R is equal to the slenderness ratio, right? So we can get rid of all those and just say slenderness ratio. That'll make it a little bit easier to write things in. So we've got 36,300 psi times, in parentheses, that was ugly, times, in parentheses, 1 minus 83.2 squared over 2 times 126 squared, close brackets, gives us a critical stress of 20,389 psi. All right, once we have the critical stress, we want the critical load. We go critical stress times area gives us 20,389 psi times 50 inches squared gives us 1,019,465 pounds. All right, and then go ahead and do our last one, our 50-foot column. Slenderness ratio is equal to KL over RY, gives us 1 times 600 inches over 1.44 inches, gives us a slenderness ratio of 416. 416 is greater than C sub C, so that tells us that this is a long and slender column. All right, so for a long and slender column, the critical stress is equal to pi squared times Young's modulus over KL over R squared. So again, KL over R, right? That is just the slenderness ratio. So we can just say SR. That becomes pi squared times 29 times 10 to the 6th all over 416 squared. That gives us a critical stress for the 50-foot column of 1656 psi. Once we have that, easy enough to get the critical load. Area times critical stress, 50 inches squared times 1656 psi gives us a critical load of 82,818 pounds. So if we go ahead and check our work, we see that as the column got longer, it buckled at a lower and lower force every time, which makes sense. That's what the theory would have told us. So it's a good dummy check on our answers. All right, so if you're looking ahead at the buckling workshop, right, it follows mostly the same process as this. The only difference is for that one, you have a web section instead of our nice rectangle. So while we were doing our rectangle, it was really easy to get Ix and Iy. It's a little more complicated to do Ix and Iy for your web section. However, you should have had some practice with that already. But once you have that, the rest of the process should be exactly the same. All right, thanks.